All right, let's jump right into this explainer. Today, we are navigating the AI hill. We're going to completely demystify that black box of how a neural network actually trains, and we'll do it by using a continuous, real-world journey metaphor. Honestly, it makes the super complex math behind this stuff surprisingly intuitive.
So if we truly want to understand neural networks, we have to ask ourselves one massive fundamental question. How do we actually guide this system down a treacherous, bumpy hill to reach the lowest possible error rate, all without it just blindly memorizing the terrain along the way? It's a huge challenge.
To figure this out, we've got a clear roadmap for our explainer today. 1. Meet the smart navigators. 2. Advanced adaptive optimizers. 3. Applying the brakes. And 4. Real-world regularization tricks.
Let's kick things off with Section 1. Meet the smart navigators, the engines of AI learning.
So what are these navigators? Well, formally, the source material refers to them as optimization algorithms. Their one and only job is to decide exactly how much and in which direction to nudge a neural network's weights. They figure this out by looking for the gradient, which is essentially just a steepest downhill signal. Without these algorithms acting as our engine, our AI vehicle, it'd be completely stuck or moving agonizingly slowly.
Looking right at the source blueprint here, you get a real feel for the foundational math tools used for this kind of complex navigation. It looks like a lot, but let's actually break these down one by one.
Okay, notice the contrast here. Let's start basic with stochastic gradient descent, or SGD. It is honestly just like rolling a ball down a hill. It takes these small steps downhill using a mini batch of data each time. And because it only checks one spot at a time, it's fast and it's simple. But think about it. If that hill is bumpy, that ball is going to zigzag all over the place on a really chaotic, noisy path.
Because basic SGD zigzags so wildly, engineers decided to add something they call momentum. The best analogy here is pushing a heavy shopping cart down that same hill. Instead of reacting to every single tiny pebble, it adds a memory of its past steps. It actually gains velocity from your previous pushes, which smooths out those little valleys and builds speed when the path is clear.
But basic physics aren't always enough for really messy landscapes. That brings us to Section 2, Advanced Adaptive Optimizers. Basically, high-tech GPS for tricky terrain.
Enter ADAM, which stands for Adaptive Moment Estimation. This takes that shopping cart momentum and combines it with adaptive steps. It acts exactly like a smart hiker equipped with a top-tier GPS. If the path gets steep, the GPS tells our hiker to take bigger strides. If it flattens out, they take smaller ones. By actively using moving averages for both the direction and the size of the gradient, it's absolutely incredible for navigating messy landscapes.
Then, alternatively, we have RMS prop. This one really shines with non-stationary problems that have constantly varying scales. Imagine driving an off-road vehicle across completely different terrains, where the system automatically adjusts the wheel speed based on a moving average of the squared recent bumps. It normalizes your steps so the vehicle doesn't just spin out of control the second the landscape changes.
Now, if we look at modern AI training, ADAM-W is usually the absolute go-to. You can think of it as ADAM on steroids for fitness. It keeps those brilliant adaptive steps, but it entirely separates out the weight decay, meaning it actively shrinks the weights over time so the model doesn't get too bulky. It keeps the whole system lean and stops it from overfitting.
So, putting it all together, this basically summarizes our vehicle's entire navigation toolkit. It perfectly matches each complex mathematical approach to its real-world analogy. You've got the rolling ball of SGD, the shopping cart of momentum, the smart hiker of ADAM, and the auto-adjusting wheels of RMS prop.
Okay, so we've got our engines running perfectly, but going too fast without control is a recipe for disaster. Let's move into Section 3, applying the brakes to prevent the memorization trap.
Here's the massive danger when training an AI. If our vehicle just memorizes the specific, exact layout of the bumps on this one particular training hill, it is going to fail completely the second we drop it onto a brand new hill out in the real world. This is a super dangerous trap, and it's known in the industry as overfitting.
To combat overfitting, we rely on regularization. These are clever tricks designed to stop the model from just memorizing the training data. Regularization acts as our crucial brakes. It stops the system from fitting itself to useless noise, forcing it instead to learn the actual underlying general patterns.
And if we look directly at this excerpt from the source material, we see the exact normalization and augmentation methods engineers use to keep these models robust and general. Let's actually unpack the coolest ones. This brings us to a really brilliant concept called dropout. During training, the system randomly turns off a certain percentage of neurons, let's say 20%. Think of it like a sports team where the coach randomly benches a few star players at every practice. Suddenly, the rest of the team has to adapt and figure out how to succeed without them. This forces the whole network to become incredibly robust, essentially creating a solid ensemble of mini-networks, instead of relying on a few fragile, overpowering connections.
Next up is weight decay, which we actually touched on a minute ago with Adam W. This operates like a strict diet for the network. Every single time the network updates, this trick subtracts a tiny bit extra, proportional to the size of the weight. By constantly penalizing the biggest weights, it slowly shrinks them down towards zero. This keeps the overall model remarkably simple and significantly cuts down on that overfitting risk.
Which brings us to our final stop, Section 4, Real-World Regularization Tricks for Consistency and Generalization. Let's look at how we guarantee our AI vehicle can handle diverse, messy, real-world environments.
First, here's batch or layer normalization. This means normalizing your inputs so the mathematical activations don't just randomly explode into massive numbers or vanish entirely. It's exactly like standardizing your ingredients before you cook a meal. If you make sure all your vegetables are chopped to roughly the same size, the recipe is going to cook evenly and consistently, every single time. It dramatically speeds up training and even introduces a tiny bit of helpful noise.
Finally, we have data augmentation. This is such a great hack. It's where we artificially expand our dataset by taking the training examples we already have and just tweaking them in simple ways. We might flip an image, rotate it a few degrees, or add some static noise to an audio clip. We get all this variation without actually needing to spend millions of dollars gathering brand new data.
To really put that into perspective, imagine teaching a toddler what a cat is. You wouldn't just show them one perfectly lit, straight-on photo, right? You'd show them that same picture upside down, or zoomed in on the paws, or maybe a little blurry. Doing this helps the AI completely generalize the core concept of a cat to absolutely any real-world variation it might bump into later. So as we've seen today, building powerful AI isn't just about raw speed. It requires this incredibly precise engineered balance between optimizing our path forward with our engines and using regularization as our brakes to hold ourselves back from just memorizing the noise. But it definitely leaves you with a fascinating thought. Now that we actually know how to perfectly balance the engines and the brakes, what entirely uncharted territories are these smart navigators going to conquer next?